Hi, folks. My name is Tom Kunzelman. I'm a professor of chemistry here at Spring Arbor University. Welcome to Spring Arbor University. We're here in the studio, and I'd like to welcome you to, this is our 11th Halloween in the Science Lab. And this year we're coming to you virtually. So welcome and thanks for joining in. We're going to do a lot of science experiments today. They're going to try to be Halloween themed. And I'm also going to try to do a lot of experiments that you can do at home with adult help. Any of the experiments that I do here that I think you can do at home, I'll make sure to say that. And I'll try to remind you that, when you do try experiments at home, you need an adult to help you. So let's get started. It's Halloween time. It's one of my favorite holidays because I get to dress up. I get to act like I'm something different. I'm a scientist. But today, I get to dress like a wizard. I love pretending I'm a wizard, and I like to do that because in a lot of ways, science, well, it's like magic. Now, there's a difference between the two, and I'd like to talk to you just a little bit about the difference between science and magic before I get started. You see, when a magician does a trick, the magician never tells you the secret behind the trick. A scientist, on the other hand, whenever they do a trick, well, we call them experiments. Sometimes they look like tricks, but whenever we do an experiment, we always do as best as we can to tell you how to do the experiment and what's going on to make the experiment work. So let's start. Let's do this one right here. What I have here is a tea bag. Maybe you've seen someone cook some tea before. I'm just going to take this tea bag and I'm going to cut the top off like this. And then I'm going to empty out the tea leaves into something that I can then throw out a little later. All right. And I'm going to open up the tea bag in a tube like that. We'll place it on the desk and we're going to hope this works. Lumos. Wingardium Leviosa. Isn't that a neat trick? There's some science behind that, and I'd like to tell you a little bit about what's going on. You see, when things burn, oh, there it goes, coming back down. When things burn, it causes air to rush toward the thing that's burning, and then that air gets hot and it moves up. It creates an air current, and it's that air current that caused the tea bag to rise after it started burning. Isn't that neat? We're going to do a lot of experiments today that deal with the air. And maybe you wonder what air is. Air is all this stuff around us. Was there really stuff there? Or is it empty? I mean, is this just empty things all over here? Or is there something there? Well, here's an experiment I'd like you to try to see if you might guess if air is made of something or not. I want you to wave your hand back and forth like this. No, don't do it like this. You might hit your sister. Do it like this. Do you feel something on your hand? I do. I feel something. I can't see it, but when I move my hand really quick through the air like this, I can feel something. And that tells me there's something in the air. And we want to do some experiments with the air because there's something there. So let's try this. I have some water in this cup. I cut out a circle from a styrofoam plate. I'm going to take this, I'm going to push it hard against the water in the cup. And I'm going to continue to push hard and turn it upside down. And then I'm going to try to remove my hand. Look at that. Aqua No Droppa. What's going on there? How can I do that experiment? It's like magic, but it's science. Here's what's going on. Air pushes. The way we scientists talk about air pushing, we say that air has pressure. Pressure just means something gets pushed on something else. And what's going on in this experiment, when I push hard on the cup like this, what I'm actually doing is I'm making it so the air pressure inside the cup is lower than the air pressure outside the cup. And different parcels of air, different packets of air, they can push differently. And if the one in the outside, the air on the outside pushes harder than the air on the inside, well, then it's going to win the push fight. There's always push fight between packets of air. Sure enough, the air on the outside is pushing harder than the air on the inside. Let's try this one more time. Pour this into this cup. See if I can't get it to work with this cup. Place it on the top. And oh my goodness. What in the world is going on there? The water's trapped. How did that happen? This experiment would be impossible on the moon. Because see, the moon doesn't have any air. It happened here on Earth because, well, our Earth has air. And there's a little secret here I want to show you. There's a net that I placed there. Now this net allows me to pour the water back and forth. And it's a little complicated to describe how this actually works. But nevertheless, it's still this idea that air pressure on the outside is pushing harder this way than the air it can push on the inside. And the air on the outside wins the push fight. That's pretty remarkable. If you'd like to try this experiment on your own, I got this net at the fabric section in Walmart. They have this sort of net fabric that you can purchase. All right, give me the next set of experiments is going to deal with the different parts of the air. And that may sound a little goofy to you, that air has parts. But bear with me and let me talk to you about it a little bit. See, the air is made of a lot of different types of really, really tiny little molecules. They're so small you can't see them. That's why the air is invisible. But the air is made of these little tiny particles called molecules. And not all of those molecules are the same. Some of the molecules in the air are made of what we call nitrogen, molecules of nitrogen. And we sometimes symbol nitrogen gas, as a capital N with a little subscript 2 behind it, because nitrogen gas is made of 2 atoms of nitrogen hooked together. So this is part of the air, and actually this is the part of the air that makes up most of the air. 4 out of every 5 molecules in the air, if we could capture them and count them, about 4 out of every 5 of them would be molecules of nitrogen. So most of the air is nitrogen. There's another part of the air that I'm going to talk about. We'll do experiments with all of these. Oxygen. A lot of people think that the air is all oxygen, but it's not. About 1 out of every 5 molecules in the air is made of oxygen. And then there's some carbon dioxide that's in the air. And we'll do some experiments with carbon dioxide as well. There's just a little bit, just a smidgen of carbon dioxide in the air. But the amounts of all of these different types of gases that are in the air are important. They're very important. And it's important that those amounts stay in balance. We want to keep them about the level where they're at. We don't want them to change a whole lot, because when those change happen too quickly, we can run into problems. So let's do some experiments with the first gas, nitrogen. And to do that, I'm going to go over here to this big container. And I'm going to pour out of this big container a liquid. And the liquid that's in here is nitrogen. That might sound a little goofy. I just got done telling you that nitrogen is a gas. Let's pour it in. There we go. Woo! There we go. I filled this cup with nitrogen. Now, nitrogen is usually a gas. We know that because it's in the air. But if you get nitrogen cold enough, you can actually get it to form a liquid. You got to get it really cold. This is minus 321 degrees below zero. That's really cold, minus 321. So actually, if you got the air that cold, the air would become a liquid. That sounds really goofy, but that's what happens. And we can do some experiments with this nitrogen because it's so cold. One that I like to do is I like to test the masks that I wear. You know, we have to wear these masks to keep each other safe. And I can do a little experiment here to show you why that's so. When we speak, we breathe out little tiny liquid droplets of water. You might have heard water called H2O before. And some of the particles that make us sick, called viruses, they can live or be embedded. I don't want to say live. They're embedded inside those particles of water. And those water particles can spread out all over the place. And that's why we wear these masks. Watch. I'll do a little experiment here. I'm going to talk into this cold air above the nitrogen. It's kind of like breathing on a cold day. When I do that, you can actually see some of these little tiny particles that we breathe out, and that can get spread all over the place. Let me do that one more time. I'll even cough. So you notice by doing this experiment, like breathing on a cold day, you can kind of see how your breath carries around and how what you breathe out might get spread all over the room and could potentially make people sick if you're sick yourself. Now let's test it with the mask on. I'll do the same experiment. I'm going to breathe out. Not quite as much spread, was there? Now I'll cough. That's a big difference, isn't there? My mask, although it's not working perfectly, it certainly works better than if I have no mask on at all. And that's why it's important that we wear masks to try to keep each other safe. There's some other experiments that we can do with nitrogen. One of them that I'll do is I'll try to see if nitrogen helps things burn. I'll do that by lighting this candle. Let's see if we can get it. Sure, there it's lit. And the fact that that candle's burning tells me there's something in the air that's helping it burn. I wonder if it's nitrogen. Let's pour a little bit of the nitrogen vapor on the candle and see if it burns better. Oh, I don't think so. I think it put it out. Let me light a few more and just double check to make sure that this is actually right. Get that one lit, this one lit, this one lit, and this one lit. And let's see if it's nitrogen that helps things burn. Oh, I don't think so, do you? Those candles went out when the nitrogen gas flowed onto it. So I don't think it's nitrogen in the air that helps things burn. You know, let's test if it's oxygen, because that's the next most abundant gas in the atmosphere, oxygen. 1 out of every 5 molecules in the air is oxygen gas. And we're going to make some oxygen gas using an experiment you can do at home. Just get a little flask or a bottle. You're going to take some hydrogen peroxide. This is found at, well, I bought this at Hutch's here in Spring Arbor. You can get it at a pharmacy. And then I like to use quick rising yeast. You see, yeast is actually a living thing. And all living things have in them something called an enzyme. It's just something in your body, a molecule in your body. And that enzyme in all living things, yeast, you, me, your dog, your cat, they have an enzyme that gets rid of this stuff because this stuff is bad for living things. That's why you stick it on a cut. You stick it on a cut because you're trying to kill the bacteria that's alive that could cause an infection. And the stuff that's in here is, I mean, you have to use a lot of this stuff to hurt you. So I'm going to pour a little bit of yeast into here, and it's going to break down the hydrogen peroxide, and it's going to form water and oxygen gas. You might notice some bubbles in there. Anytime you see bubbles, you know a gas is being formed or released. I see those bubbles, and those bubbles, that represents the yeast in the the enzyme in the yeast breaking the hydrogen peroxide down into oxygen gas and water. It's the oxygen gas I want. I'm trying to fill this container, fill this flask with oxygen gas. And the reason why I'm doing that is I want to see how this wood burns in what's essentially pure oxygen. This flask now is filled with oxygen gas. So what I'm going to do, I'm going to get this wood splint burning. We kind of see how it burns in air, but I'm even going to blow it out. And you'll notice it might be glowing just a little bit. Just a little bit. So the splint is glowing in the air. And I'm going to plunge it into this pure oxygen and see what happens. Whoa! Did you see that? This is how the splint's burning in air. Let's see how it burns in pure oxygen. That's pretty neat. Hey, that reminds me. That looks like a wand, doesn't it? Lumos! Did you hear that pop? Let's try it. It doesn't always work, but sometimes when I do this experiment, I'll hear a little pop. And that's a tiny little explosion when the wood splint bursts into flame very quickly. Let's try it. I'm going to plunge it in here. Let's see if we can get the little tiny explosion. Could you hear that? Just a little pop. I was able to hear it. Oh, that was a good one. So I guess it might be oxygen in the air. Might be oxygen in there that helps things burn. I think maybe. I think that might be the case. I want to do another experiment with oxygen. I didn't do this last time. A burning experiment. Let's try this one. What we're first going to do is just what we call the control experiment, the normal experiment, without doing something different than what would be normal. I'm going to take a little piece of this paper towel. I'm going to place it on this piece of metal. We're going to light it on fire and see how it burns in air. So there's oxygen gas that's helping that burn. Now what I'm going to do is I'm going to try to take a lot of oxygen out of the air, and I'm going to soak it into the paper towel and then light that on fire. And here's how I'm going to do it. I'm going to take this metal pan, and I'm going to fill the pan with liquid nitrogen. Let's see what happens when I do that. Okay. I'll put this on because liquid nitrogen is really cold. I probably should have, just hold on, I should probably have a paper towel ready. This is a little tough to pull off, but it's worth the wait. Okay. Yeah, that's going to work. So I'm going to pour this liquid nitrogen into this pan, and this is going to cool the pan down a lot to minus 321 degrees Fahrenheit. That's really cold. And it's actually so cold that when oxygen gas from the atmosphere hits this, it turns to a liquid. You see that stuff dripping down? Clayton, you able to catch that on video? Right there from the corner? It looks like rain, it looks like water, but it's not. It's oxygen gas. That's crazy. This pan is so cold that when oxygen gas from the air hits it, the oxygen turns to a liquid. This is one of my favorite experiments to do. Okay, now what I'm going to do is I'm going to try to soak this paper towel with what I'm claiming is a liquid. Because I know some of you are saying, no, that's just nitrogen leaking out of the pan, or that's just water dripping down. Well, we know water doesn't help things burn. And I just showed you some experiments that show you that nitrogen doesn't help things burn. Now I'm going to drip this oxygen into this paper towel, and I'm going to light it on fire. It takes a little while, so let me get this soaked. I want to get this soaked as much as possible with the oxygen gas. Excuse me, I said oxygen gas. I want to get this soaked as much as possible with liquid oxygen. And then we're going to try lighting that thing on fire, see what happens. Dr. K says that's oxygen. I know some of you don't believe me. Let's see. Here we go. Holy mackerel. That's a little bit different, wasn't it? Yeah, that's some evidence. We know that oxygen helps things burn. And the fact that this drippy stuff here helped make that paper towel burn tells me that probably was oxygen pouring down from the pan. That's kind of neat. You might remember that I said that hydrogen peroxide is bad for living things. This stuff here. So why in the world do we stick that on a cut? Well, when you get a cut, you want to kill the bacteria that might cause an infection. And the stuff they use here, only a little bit of this is hydrogen peroxide. If you know your percents, 3% of this is hydrogen peroxide. The other 97% of this is water. And they use really low concentrations, really low percent, 3%, because they don't want to hurt you. They just want to hurt the bacteria. Well, Dr. K is able to get hydrogen peroxide that's 10 times as concentrated, 30%. So we can make 10 times as much oxygen using the 30% hydrogen peroxide. And for this, I got to wear my gloves because I don't want to get the hydrogen peroxide on my skin because that would hurt my skin. Okay. Now, I'll take this here and some 30% hydrogen peroxide. You can see it there on the bottle. And we'll pour some of this in. Got my goggles on, okay. Well, that looks pretty good. I'm going to add a little bit of detergent because I want to catch the oxygen that's made in foam. So we're going to add a little detergent so I can catch it in a foam. And then we're going to hope this works. I'm going to add something that's going to convert the hydrogen peroxide that's in here into water and oxygen gas. And that oxygen gas will hopefully get caught in the foam. Let's see. Oh, look at that. Beautiful. You can see some water steam coming off. A lot of foam. Hey, Dr. K, you told me there's oxygen in that foam, and oxygen helps things burn. Let's test that. Let's test that idea. So what I'm going to do is I'm going to get this wood splint lit, just like I did before. I'm going to get it glowing. And we're going to stick it down in the foam. Oh, look at that. Looks like I got another Lumos potion. Lumos! Sure enough. Let's try it down here in this, see if it, oh yeah, look at that. Beautiful. Oxygen really helps things burn, doesn't it? It sure does. I talked about nitrogen being in the air. We know that that doesn't help things burn. Well, okay, I remember that. And then oxygen's in the air, and that does help things burn, yeah? Let's do the same kind of test with the next gas we're going to test, carbon dioxide. Let's make some carbon dioxide and see if that helps things burn or not. And we'll make this in a way that you can do at home. You may have already done it in some of your classes. Well, maybe not this way. I like to get a big tub. And I'm going to make a lot of carbon dioxide gas in this tub. My fun way of doing it. And if you have ever mixed together baking soda and vinegar, what do you see when you do that? Have you ever done it? Some of you may have. You get bubbles, right? That's how you make the volcano. Sometimes people like to make a volcano by mixing together baking soda and vinegar. Oh, there's a lot. Punch that up. I'm going to pour in the vinegar. Let's see what happens. I hear fizzing. I see bubbles. There's a gas being released. And that gas is carbon dioxide. Carbon dioxide gas. Dr. K is now going to test to see if it burns. I wonder how much we've made. Get this candle lit. I'm going to slowly lower the candle into the tub of carbon dioxide gas. Oh, look at that. It's out. I just moved it down that far and it went out. There's carbon dioxide gas that's rising and filling this container. Let me try that one more time. Here, let's do it with a splint. That might actually be a better way to do it. Got a nice flame going there, don't we? Yeah? Let's plunge it down in. Out it goes. Out it goes. Hey, that was cool. Let's do that one more time. Oh, look at that. You can even see, I think you can even see a layer. I can see a layer of smoke there. I've never seen that before. That's kind of cool. I wonder if that layer of smoke is kind of riding on top, floating on top of the carbon dioxide gas layer that's formed. Sorry, I've just never seen this before, so it's kind of interesting looking to me. This happens every once in a while while I'm doing experiments. Beautiful. Looks like a cloud, doesn't it, folks? Well, that's gorgeous. I'm going to have to play around with that later. Okay. Just going to try to get rid of it here a little bit for the next part of the experiment. What I'm going to do next, I'm going to blow a bubble in there. And the reason why I'm blowing a bubble in there is I'm testing a property of carbon dioxide gas. You see, they tell us that carbon dioxide is more dense than air. And what that basically means is if you have a parcel just of carbon dioxide gas, and that's in the air, it should sink in the air. You see, because things that are more dense than air are going to sink in air. Like things that are more dense than water, sink in water. Things that are less dense than air float in air. Things that are less dense than water float in water. It's kind of easy to remember. The less dense you float, the more dense you sink. They tell me that carbon dioxide gas is more dense than air. That means the carbon dioxide gas that's been formed in this container should stay sunk in this container as long as I don't disturb things too much. Well, let's see. Carbon dioxide, that's more dense than air. And a lot of what I exhale is air. Let me exhale some air into a bubble and see if the bubble is more dense or less dense than carbon dioxide. Oh man, I wonder what happened there. I'm gonna have to make it a little bit more. Let's see. Oh, there it goes. Look at that. Sure enough, the bubble is less dense than the carbon dioxide that it's floating upon. I can't see the carbon dioxide. Can't see it. But this experiment's not going to work without the carbon dioxide in there because we can see what happens to bubbles in air. Let's watch. We all know bubbles sink in air. Down it goes. All the way to the ground. But in carbon dioxide, the bubble floats because the bubble is less dense than the carbon dioxide. And the carbon dioxide stays in the container because it's more dense than the air. It stays sunk in the surrounding air. Let's do another one. That bubble's staying a good long time. I like that. Oh, goodness. There we go. Bunch of them in there. I'm going to try one more thing. Let's try another thing. Let's scoop the carbon dioxide out. Let's get it out of there. Whoop, whoop. Okay, here we go. Ready? I'm going to scoop it out. This is not voodoo. This is science. It looks like magic, though, doesn't it? Let's make a great Halloween magic trick for some of you who might want to do that tomorrow. Okay. Do you think I've scooped all the carbon dioxide out? Let's find out. Let's find out. I don't know if I did or not. Here's my test. Oh, gotta work on my bubble technique. No, look at that. The bubble sank because I scooped all the carbon dioxide out of the tank. And when that happened, it got replaced with air, and we see that bubbles sink in air. What is dry ice? Well, regular ice is made of water. This is dry ice. See, regular ice, it's made of water. Water's good old H2O. And water melts, so it gets wet. This ice here, it actually doesn't melt. That's goofy. Ice that doesn't melt, what's going on there? Well, dry ice is made of carbon dioxide. It's made of something different than the ice that you stick in your glass. The ice that you stick in your glass to make it cold is made of water. This ice is made of something different. It's made of carbon dioxide, and it behaves differently. So if it doesn't melt, let's see, if it's melting, it goes from a solid to like a liquid, doesn't it? So this isn't going to a liquid. I wonder what it's going to. I'm going to do an experiment to find out. Let me take this here, and I'm gonna pour some water in here. And then I'm going to get my glove on because this stuff is really cold. It's not as cold as a liquid nitrogen. I'm going to drop this in here and see what happens. Hey, what do you see? I see a whole bunch of stuff. I see bubbles. I see something that looks like a cloud up here, don't you? But yeah, I see bubbles. And those bubbles tell me that a gas is being released. Anytime you see bubbles, you know a gas is being released. So that must mean that if this doesn't go from a solid to a liquid, maybe it goes directly from a solid to a gas. Yeah, I think that's what's happening. We call that process, something going from a solid to a gas, we call that, it's a big word now, we call it sublimation. Like a submarine, sublimation. Sublimation is what carbon dioxide does. And it makes this beautiful Halloween effect. I mean, a lot of people play with this stuff for Halloween because doesn't that just look like a witch's cauldron or something like that? Well, maybe a witch's test tube. I guess that's not a cauldron, is it? But we can do the witch's cauldron effect. This is a lot of fun. We're going to try this. What I'm going to do is I'm going to get a big 5-gallon pail. And I'm going to pour some hot water in this. The hotter, the better. And I'm going to dump some dry ice in here. And then what I'm going to do is I'm going to take this soapy towel and I'm going to rub the soapy towel over the top in a way that I hope I can get a thin bubble film on here. Let's watch what happens. Okay, here's my dry ice. A bubble film, that looks like a witch's cauldron. Sounds like it too, doesn't it? Yeah, all that bubbling, that's from the carbon dioxide undergoing sublimation. Hope I can do this, folks. It's fun if it works. I think I might have it. Nope, it's still spilling over the side. Come on. Come on, Dr. K. You can do, oh, it broke. I had it. Try it again. There it goes. It's working, it's working, it's working, it's working. Come on. Oh, shoot, it keeps breaking. The water might be too hot. Try this one more. You know what? Let's get a little more soap. Let's try that. Try a little more soap. Dump that in there so you can get a little tougher skin. Oh, I hope you get to see this. hope you get to see this. It's so much fun. There it goes. There it goes. Look at that. That's goofy. Isn't that fun? I do that at Halloween. People are going to have a great time. Just blow just real gently on it. It's like a blob. Happy Halloween. Boom, there it goes. Let's try that one more time. See if you can get it. You notice I noticed the lip of this tub is a little different than the one that I was using yesterday. I think that's likely why I'm having a little bit of trouble. Actually, though, when I used a bunch of soap, it works pretty well. You might also notice like a rainbow of color on the bubble. That rainbow of color is a similar effect to a regular rainbow. You see, when light comes through little tiny droplets of water, the droplets of water split the light into all the colors of light. And the same thing is going on here. The film, the thin film of the bubble fluid is splitting the light into all the colors of light. All the colors of light make up white light. Let's blow on it a little bit. We need some music. Woo! Let's do that one more time. Then there's one more experiment I'd like to do with carbon dioxide. How are we doing on time?
11:37.
Oh boy. I won't charge you for the extra experiments. Is that okay? We won't charge you extra. I didn't charge you anything to begin with. I hope you're having as much fun doing these experiments as I am. Boy, I've made a mess. I want to get my finger soapy first before I try this. I'm touching a bubble. Look at that. Don't do that with a dry finger. It probably won't work. If I can pull it away. Whoop, look at that. Try that one more time. Do it with a soapy finger. All my fingers are soapy. Come here, you. Look at that. Isn't that fun? Oh, man. Somebody send me a picture of that by email if you do that. I'd love to see somebody actually try that at home with adult help. So when this last experiment is also going to deal with carbon dioxide, and I'm going to use dry ice for this particular experiment. And this last experiment has to do with how our air is changing. And see, the amount of nitrogen and oxygen and carbon dioxide that's in our air, it stayed the same for a really long time. And life on Earth, people, have gotten used to a certain amount of carbon dioxide and oxygen and nitrogen in the air. And what's happening as people burn stuff like wood or fuel for a car or fuel to heat your home, you know, these are important things that we do to give us energy to do a lot of different things, turn on the lights and things like that. We say we burn fuel, usually carbon-containing fuel. Sometimes we call them fossil fuels. And when that happens, carbon dioxide gets released into the atmosphere. And it's actually turned out that the amount of carbon dioxide that's been released into the atmosphere has changed as a result of people doing this for, you know, about 200 years. And that's kind of important because carbon dioxide helps to regulate the temperature of the Earth. It's remarkable. If there was no carbon dioxide in the air, Earth would be an ice ball because carbon dioxide helps to warm a planet when the carbon dioxide's in the air. So what happens is if you don't have much carbon dioxide in the air, the temperature of the planet tends to go down. If you have a lot of carbon dioxide in the air, the temperature of the planet tends to go up. The hottest planet in the solar system is Venus. It's hotter than Mercury, even though it's further from the sun. And that's partly because Venus has an atmosphere that's almost all carbon dioxide. It's really hot on the planet Venus, too hot for life. So it turns out that the amount of carbon dioxide in the atmosphere, it's important to keep that in balance. And we're tending to start to get that out of balance a little bit because of the use of fossil fuels as an energy source. There's another problem that comes from putting too much carbon dioxide in the atmosphere, and that has to do with our oceans. I'm going to do an experiment here to kind of show you what this means. So our oceans have a certain acidity associated with it, which means it has a certain, what we call a pH level. In other words, there's a certain, just like everything, there's a certain balance that needs to be associated in our air. There's a certain balance that needs to be associated in our ocean. And when carbon dioxide goes into water, it actually makes the water a little bit more acidic. I'd like to show you how this happens here. I'm going to take a little bit of this substance here, and I'm going to add it to this water. This is a base. You can think of a base as an anti-acid, the opposite of an acid. And now I'm going to add an indicator. This molecule, or this substance, I should say, tells me whether this is acidic or basic. If it turns pink, we know it's basic. Aha. And if it's colorless, we know it's acidic. So because I've added this particular substance to this fluid, which is water, and it turned pink, I know that this is a base. And it turns out our oceans they're slightly basic. They're a little bit like a opposite of an acid. And there's a certain balance to that basic nature of our oceans. Now what happens when we put carbon dioxide in the atmosphere, the carbon dioxide actually goes into the water. Let's see what happens when we do this. I'm going to take some carbon dioxide from dry ice, and I'm going to drop a piece here into this water, and let's see what happens. Well, wow, we get the same effect, don't we? We get the nice cloud here, we get the bubbles, and it looks like that pink color faded, didn't it? I wonder if, well, I better get a fresh one here. I don't know which is which. Let's see if the carbon dioxide can make even more of this base go away. That was 8 drops. Huh, let's try 10. I'll cut more than 10. So I'm continuing to adding base, trying to keep that sort of level of basic nature in my flask. But as the carbon dioxide bubbles through, we can see it continues to fight against the base nature of this substance that I'm adding. Actually, this is taking a little longer. I added quite a bit, didn't I? There it goes. It's fading, isn't it? And again, this is because when carbon dioxide bubbles into or mixes into water, it makes that water a little more acidic than it was before. And the buildup of carbon dioxide in our atmosphere from the burning of fossil fuels is causing this to happen in our oceans. And some scientists tells us that in addition to the warming effect of the carbon dioxide in the atmosphere, the addition of carbon dioxide to our oceans might cause some trouble for sea life. And of course, that might cause trouble for the people who depend upon that sea life. Had a great time with you folks. I hope you all have a happy Halloween. And hopefully next year, we can do Halloween in the science lab in person. Thanks so much for coming, folks.